Okay, so today we're going to talk about something called the dot product. So the dot product is used, it can actually be used to, as an operation between geometric and Cartesian vectors. So we have actually formulas for both of them. There's a couple little pieces of information for you guys here. So dot product is also called scalar product. Basically what this is and what we're doing when we do the dot product is we're thinking about how the vectors work together in the same direction. So when I'm going to explain this a little bit more with like an actual picture in a second, but the idea is I want to know how vector components are actually working together to strengthen one another. So what we get from multiplying these vectors is a scalar. Okay, so remember when we talk vector, we're talking about like direction and magnitude. When we talk scalar, we just get kind of that magnitude component there. So the dot product is kind of like multiplying vectors so that they're working together in the same direction. That's the idea. There's a geometric and Cartesian formula, as I said. If two vectors are perpendicular, there's no components that are working together for those vectors, right? There's no part of this that's working in the same direction as this, so the dot product ends up being 0. So we want to see how those things are interacting together. So standard algebra works with dot product. For instance, if I have like a scalar, I can distribute that scalar. I can do like an associative property, like 7 times 3 is the same thing as 3 times 7. So the dot product works a similar way where I can flip it both ways, associative. It's communicative, or sorry, that what I just described is communicative. And associative. So if I'm multiplying by a scalar or I'm multiplying 3 things kind of all together, or I'm doing the dot product of those things, I can do it in any order. And it should be giving me the same answer no matter what order I do it in. Okay, so we don't have to worry too much about like the particular order in which we do things with our dot product. Okay, so I'll introduce to you guys the formulas to start, and then I want to just explain especially where our geometric formula comes from. So our geometric formula, if I want to do A dot B, again, it looks like a multiplication, but when we're talking about vectors, we say dot. It's going to be equal to the magnitude of vector A times the magnitude of vector B times the cos of theta. Okay, and this is where the vectors are arranged tail to tail. So the theta that I'm talking about is when they're arranged tail to tail. And we always talk about our theta as if it's between 0 and 180. There should be no need for us to go over 180, simply because like no matter how I draw two vectors, I'm just taking that interior angle rather than the exterior angle. So there should be no need for us to do anything over 180 degrees. So theta is going to be between 0 and 180. Okay, so I'm going to unpack that guy for you guys in a second. But for Cartesian, this is actually a little bit easier. So if we have two vectors, A and B, and I have like the x component of A and the y component of A, we usually call this like A1 and A2, although you can call it like A with a subscript of x and A with a subscript of y. But this is kind of like the standard notation. Essentially what I want to see when I'm doing the dot product is the components of the vectors that are working together. So how the x components are working together and how the y components are working together. And again, I don't get a vector from this. I actually get a scalar. It's kind of like the percentage of how these vectors are working together. So when I want to do A dot B, it ends up being the x components being multiplied, so A1 and B1, plus the y components being multiplied. So I'm interested in the sections of this vector that are working in the same direction. Okay, so essentially I multiply the x components and I multiply the y components and I add them together to get my final scalar. Okay. Question, yeah. So geometric is what we were working with last chapter. So we'll have like, it will tell us like the direction of the vector and its magnitude, whereas Cartesian is going to be expressed like this, like it would be expressed as a vector 1, 3. Yeah, yeah, exactly. So I'll show you examples of each of them, and then I think you'll kind of get the idea of why we need separate formulas. Okay, so explanation, I have a little link for you guys to check out if you want to rewatch it after. But this is the idea. So like I said, we're interested, sorry, these should have little vector symbols on them. Like I said before, we're interested in how these vector components are working together. So if I have vector A dotted with vector B, I'm interested in the parts of B that are going in the same direction of A. Or I can say it the other way around. Because it's associative and communicative, I can also look for the components of A that are going in the same direction of B, and I'll get the same answer. So imagine, I like to kind of imagine that we are shining like a flashlight from up top. So imagine we're kind of like shining a flashlight, and there's a shadow that almost gets projected from this vector onto our vector A here, and it's only going to go as far as my vector goes here. So if I'm doing that shadow, I get kind of like a perpendicular component where that light kind of ends. And the overcast shadow is usually referred to as the projection of B onto A. It's almost like the shadow of B onto A. So sometimes we call this like the B component that goes in the direction of A. And I'm interested in how this vector, this blue part of the vector, and how vector A are strengthening one another as far as like their scalar multiplication. So the question becomes, how do we calculate the B component that goes in the direction of A? That's the question, right? So here I have the magnitude of A. And this makes sense because I have this magnitude of A that I'm interested in. I'm interested in that scalar component of A. But how do I calculate this B component that goes in the direction of A? Well, if we think about this in terms of where theta is here, this B component that goes in the direction of A is actually the adjacent side, right? And the B vector is actually the hypotenuse in our blue triangle right here. So if we think about finding this B component that goes in the direction of A, we have to use cosine because I have the adjacent side and I have the hypotenuse. So if I say cos of theta is equal to adjacent, which we've labeled to be the B component that goes in the direction of A, and really we're kind of like talking about the magnitude of this B component, divided by hypotenuse, which will be the magnitude of B. So what is the magnitude of B, the B component that goes in the direction of A? Well, I can find that simply by multiplying this B component up to this side over here. And that's where I get this B cos theta from. And that gives me the magnitude of that B component that actually goes in the direction of A. And then from that, we can kind of see how those scalars affect each other as far as like a multiple, so how they strengthen one another. So this is where I get this little component of our dot product here. Mark?
So does B always have to be shorter?
No, so I can also do this in the opposite direction as well. So essentially, like, if I wanted to find the A component that goes in the direction of B, I can do that as well. So basically, again, we would kind of think about shining a light here. But you have to imagine that the shadow can actually go further. So the goal is when I'm seeing what this projection actually can do, is I want to make these two things perpendicular. So this is the A component that goes in the direction of B. And I will, if I figure that all out again, I'll get the same dot product formula. Instead, I'm just doing the magnitude of B, and then I'll get A cos theta for the part of A that goes in the direction of B. So I can do it either way. Ryan? So I'm just saying, like, you're going to think about it as a shadow. What shadow part of this B will be put onto this component of A? That's kind of the idea of shining a light. Okay? Another way to think about the dot product is to think about Mario Kart. Okay? Everybody's played Mario Kart here before, I hope. So you guys know how there's like the little like booster pads as you go and you play. So if I have like a booster pad and it's telling me like, okay, go in this direction, and you get like a little boost. Thank you. So imagine that I'm in my cart here, and I'm Toad, obviously. And Toad?
Oh, no.
Duh. Imagine that I hit this guy like this, right? Am I going to get my max boost from that? No. The maximum boost that's going to happen from that is if I am working in the same direction as that pad, right? And then I'm going to get that scalar multiple of speed where I have my speed, and then it gets multiplied by me working in the same direction here. But this is kind of only going to work as well as these two things are working together. So if I'm not hitting this at the exact right angle here, if they're not at the same angle, then I still have a component of that that's working with me, but I don't have that maximum like scalar component where I get strengthened that much more, right? So that's kind of the idea. Yep.
That was my other question. Why do we like multiply A and B cos theta instead of adding them?
Yeah, so we want to know how much, as far as like almost like a scalar multiple, how much these are being strengthened with one another. So dot product is a multiplication of vectors, but it doesn't happen like just as a straight multiplication. So it's actually like multiplying the scalar components and seeing like almost a percentage increase for how these can strengthen one another.
So does it actually like represent anything in the real world?
So the applications will be different based on like, the implications will be different based on what we're calculating. So you can use this to calculate work, for instance. So I'm going to show you guys some applications of this. Okay, but the units, it's hard to explain without units because it's different depending on what we're working with. Okay, so essentially this explanation here, if you want to rewatch it, you can go to this YouTube link, but it's basically the same. Okay, so these guys right here, these are our geometric examples like Zainab was asking me about. So these are what we'll use the first geometric formula to figure out here. So let's start with A. So these vectors are already arranged tail to tail. That's what I want in order to use my geometric vector. And again, I'm imagining here that I'm shining a light and I want to know this component of B that gets reflected onto A. So imagine that this is being reflected over here, and I want those components to make a right angle. So I want to know how much of that component is being shone onto A. Or we can do it in reverse as well. It doesn't matter. So A dot B, in our case, will be equal to the magnitude of A times the magnitude of B times the cos of these angles, or the cos of these vectors when they're arranged tail to tail. So really, I'm doing 20 times 30 times the cos of 40. And that will give me, again, it's a little bit hard to understand if we're not doing an actual application, so it will make a little bit more sense when we actually apply this as far as like units, but we want to see how these vectors strengthen one another. So what'd you guys get?
4, 5, 9, 6.
Right, great. Okay, and again, the resultant here that we get, or maybe not resultant, but the result that we get here is a scalar. Okay, let's try B. So this one we don't have any units of measurement. The units of measurement will vary based on the application, but for this one, we're not going to put any units. Okay, for part B, you're going to notice We talked about what happens when vectors are perpendicular to one another. Are there any components of these that are working together at all? No, the x components are working completely separate from the y components. So watch what happens when you enter into our, oh sorry, I should have put n and m. We'll do n dot m. Again, order of these should not matter, but watch what happens when I sub these things in. I do 75 times 60 times the cos of 90, and the cos of 90 is 0. So what ends up happening is I have 0 components of this that are strengthening one another. In fact, they're working in completely opposite directions, so they're not strengthening one another at all. Okay, for this last one here, this one is kind of interesting because if you imagine that we shine a light down here, this part of my vector is actually being projected in the opposite direction of v. So if I want to know the component of u that's actually working in the same direction of v, there isn't a component that's working in the same direction. In fact, they're working in opposite directions. So are they strengthening one another or are they weakening one another if they're working in opposite directions? Okay, so I would expect that my scalar from this, if they're getting weakened, will end up being negative in this case. Yes, and cos of 120 is negative, so that should make sense. Okay, so we want to think of dot product as if it's kind of like how the vectors are working together or working against one another. Could be what we think about as well. So u here is 100, v is 85, and then we'll do cos 120. And again, because the portion of u that goes in kind of the same direction of v is opposite to v, they're weakening each other, so our dot product will be negative. Devin? So again, if we're shining a light up here, where is the shadow getting projected? Well, it's getting projected down here, right?
It could still be a line, but how do you know the arrow's pointing out?
Well, I have to arrange these guys tip to tail in order for it to add up to u, right? So it's going this way and up in order to be like tip to tail components of u.
So for A and B, could you show me like what the...
Yeah, so it's easy. It's probably easiest to show you like if I'm shining a light this way on A, I'm getting a part of this that's at a perpendicular angle to B, and this is the component of A that's working together with B. So essentially, it's kind of like these two components right there. So still tip to tail, but this is the component that's working in the same direction as B. Does that make sense? Okay, perfect. Okay, so what did you guys end up getting here for our part C? Great. So I always am using the angle when they're arranged tail to tail. Yeah. Cool? Okay, this is going to make more sense when we do an actual like example with units. You'll kind of understand what we're talking about. Okay, notice also here I didn't put the 0 vector because the answer to the dot product is actually a scalar. So I don't want to put 0 vector when I'm doing dot product. Okay? All right, so here's the deal. Based on the angle of theta, I showed you guys 3 options here. I showed you an acute option, so under 90. I showed you equal to 90, and I showed you greater than 90. So we should actually be able to make a bit of a prediction here as to whether our answer will be positive, negative, or 0. So let's first say if our theta is less than 90, this will mean the dot product is positive. Then A dot B will be greater than 0 or positive. Okay? If theta equals 90, then the dot product is equal to 0, perfect. And if theta is greater than 90, or obtuse,
Oh yeah, it's like K is greater than
So if theta is greater than 90, dot product will be
Negative.
less than 0 or negative, yeah. Okay, and that's simply because those components of those vectors are actually working against each other rather than with each other when we have that obtuse angle. Okay? Olivia. It means no vector components are working together. There's no components of those vectors that work in the same direction. So if we look at this, are there any x components of these vectors that are working together? Are there any y components that are working together? So that's what the dot product is interested in, what components are working together and how they strengthen one another. These aren't strengthening one another at all. Okay? Okay. Do we need a little break here? Okay. All right, so here's an actual example. Hopefully this helps you guys kind of understand what we're calculating here. But we have Max pulling his sled up a hill with a force of 120 newtons at an angle of 20 degrees to the surface of the hill. The hill is 100 meters long. Find the work that Max performs. Work, which is a scalar, is calculated by doing the force that's applied times or dotted with the displacement. So you will actually notice here that force and displacement are actually two different units. But we can still see how these are dotted together. My final thing, if I'm dealing with newtons and meters, my final outcome of this will be Newton meters, which is joules. Yes, it is. Thank you, Mark. Okay, so here's what we've got. We've got our hill. It's 100 meters. We have our sled. And it's being pulled up at an angle of 20 degrees with the hill with a force of 120 newtons. And this is actually my displacement right here. It's 100 meters up the hill. Okay? So we're simply interested in how these two how the displacement and the force are kind of working together. So what component of the force is working in the same direction as the displacement? And that will actually give me the work or joules that's put into dragging this sled up the hill. Okay? So far so good? Mark?
So in this unit, like, do scales really matter?
I mean, you're not going to be able to figure out work from drawing this to scale, so it's not going to be like super important. Because work is how these like components work together on a scalar level. So it's a little bit different. It's not a resultant. So if work is force dotted with displacement, we're actually getting the magnitude of the force times the magnitude of the displacement times the cos of the angle that they make together. That will give us work. So my force is 120 newtons, and my displacement is 100 meters. And then we're going to do cos of the angle that those two components make together. And then we should get our work from that. Again, it's a scalar. Great. And this is Newton meters, we say, or 100 or 11,276.3 joules. That is what Newton meters are. Okay, so there's our work. All right, so those two examples, example 1 and example 2 that I just showed you, these are geometric ways that we can use the dot product. Are there any questions on this before we move forward?
Will we always be given, like, those, with the
I think you have to be given like I mean, you could have to, if you're given the work, you could solve for displacement, I guess. But it's just division, so yeah, usually you're just given the force and the displacement though. Okay. Cartesian, how do we use this in Cartesian vectors? Okay. So we are going to calculate here u dot v. Again, order does not matter. I can say u dot v or v dot u. We'll get the same answer. Now, when I'm doing this, as far as like a Cartesian vector, the formula is a little bit different because I already have the x components and I have the y components, and I'm interested in how those are working together on a scalar level. So I'm going to take the x components and multiply them, and I'm going to take the y components and multiply them, and then I'm going to add those two scalars that I get together. So here we end up getting -1 for the dot product. Okay, for part B, if I do u dot v, I'm doing the same thing. So we're going to take the x components and multiply them, and add them together with the multiple of the y components. So here we end up getting 2. So for part A, are these vectors working together, or could I assume that the angle between these vectors is acute or obtuse or what, depending on our dot product here? It's obtuse, right? So those components of those vectors are actually working against one another. Cool. Questions? We're okay with that? Yep. That's it. Okay, guys, we've got a couple more examples. Stick with me. We're almost there. Just wait till everyone's ready here. Okay, so we are tasked with finding the angle between the vectors in example A of, or part A of example 3. So we found u dot v in example A of 3. And if I'm going to find a vector or an angle between vectors, I actually can only get the angle from one of my formulas. The only formula that has an angle between vectors is actually the geometric dot product. So the Cartesian dot product and actually the geometric dot product can actually work together to help us find different things if we need them. So the geometric dot product is equal to the magnitude of u times the magnitude of v times the cos of the angle between them. And this component right here is actually what I'm interested in solving for if I want to know the angle between these vectors. Now, magnitude of a Cartesian vector. How do I find if my u vector is 5, -3? Does anyone remember how we can find the magnitude of this vector? Yep. Okay, so I'm squaring each component and we're adding them together and square rooting the whole thing to get that magnitude. And we'll just leave this as an exact value. So you should get root 34 for that, 25 and 9. Okay, and then I also want to find the magnitude of v because that's also in my dot product formula. So v was 4, 7. And we're going to use our magnitude formula for that as well. So I'm getting 49 and 16, which is root 65. Okay, so the parts that I have, I know vector u dot v from example A example 3 part A. What did I get for u dot v? We got -1. Okay, I also know that the magnitude of u is root 34, and I know the magnitude of v is root 65. So I should have basically everything that I need in order to solve for the angle between these two vectors. So I'm just going to divide out that root 34 and root 65. And then we will take the cos inverse of this expression to get theta by itself. Okay, so just making sure we're in degree mode, we'll do that cos inverse of that expression there. Yeah, Mark? It's okay. -1 was just our answer from part A above when we calculated up here. Yeah. What'd you get, Zainab? Great, so we'll just say 91.2 degrees. I think that's good. Awesome. So now we know the angle between two Cartesian vectors. Yep.
Sorry, random question. Are there decimals in true bearing?
Yep. You can have them.
But do you have them?
This isn't necessarily true bearing. It just says however these vectors are rotated. It's just telling us that this is 91.2.
I'm just asking for like when they ask.
Yeah, you can have decimals. If it's less than 100, though, you would have the 0 in front of it still. Yeah. Okay, great. Last question. Use an example to prove that A dotted with itself is actually equal to the magnitude of A squared for any vector. Okay, so we're going to just choose an arbitrary vector here. Let's say we use the vector 3, 5. Okay, again, I'm just choosing a vector A. That's what part A tells me to do. And we're going to see if A dot A is equal to the magnitude of A squared. So we're going to have to solve A dot A and also magnitude of A squared. So let's start with A dot A. We'll call that kind of like the left side, and then we'll do the right side. So A dotted with itself. A dotted with itself means I'm doing the x components multiplied by one another, which is 3 and 3. And I'm adding them to the y components multiplied together, which will be 5 and 5. So here I'm going to get 9 plus 25, and that gives me 34. Okay, magnitude of A squared. Well, if the magnitude of A is found like this, where we do the square root here, I could actually just square both sides and just do the x component squared plus the y component squared. So essentially, if I have this squared here, we want to think about our x component of A squared plus our y component of A squared. But I also have to, if this side is squared, we're thinking about squaring this side, right? So that squared and square root kind of cancel each other out there from how we're used to calculating that magnitude. So magnitude of A squared will just be this x component of A squared plus that y component of A squared. So we're getting the same thing if you notice over here. This is like 3 squared and 5 squared. So we actually get, oh, sorry, this is squared. We get 34. And I know you guys missed left side equals right side, so we'll just do that for fun. Think back to trig identities, right? Reminisce.
Did that on my last flip chat.
Did you?
Yeah.
It's like, what side equals this?
Yeah, on our
When are we getting a test?
Soon, yep. I'm just totaling them up. Okay, last part of this. So we've proved this for one example, one single example. We want to prove this for all examples, okay? So the idea is that no matter what vector I have, I would like to prove algebraically that if I dot that vector with itself, that it's going to be equal to the magnitude of that vector squared. Okay, so how can we prove this in a more general sense? Okay, so again, we can do kind of a left side, right side thing. algebraically. So if you want, we'll set up left side, right side again. Okay, and here's what I want to think about. Let's think about vector A as if I have the x component, or we also called this like A1, so whichever one you're happy with. And then I have that y component, or A2, if you want to call it A2. Okay, so what happens when I have two of these? Well, when we dot them together, we get our x components being multiplied. So we get our ax times our ax plus those y components being multiplied together. So our ay times our ay. And essentially that's ax squared. Agreed? Ax times ax squared. We're good with that? Okay. So we're going to say this. Good? We're all okay with that? Makes sense? Okay, and then like we said, magnitude of A squared, we know because the magnitude of A is actually equal to, we'll move this guy out of the way, is actually equal to ax squared plus ay squared. If I have magnitude of A squared, I just need to square both sides, right? So I square this, and I square this, and I've got that ax squared plus ay squared. Mark?
Couldn't you just go A times A equals 0?
A times A cos 0.
'Cause it,
Yep.
yeah.
Yep, that's essentially what we're doing. So all parts of that vector are working in the exact same direction, right? So we actually get like I was talking about with your Mario Kart ramp or your Mario Kart booster, we get maximum strength from those two vectors working in the exact same direction, right? Okay, so this is being proven now for all general vectors. We can see that if we dot those vectors together, we get something that's equal to that magnitude squared from the length formula that we have.
So when you say like you get through the A times A equals 0 thing,
So when you're doing, so this is like we're kind of proving it geometrically. But yeah, we can show that the cos is 0, so we get 1 for cosine, and then it's equal to A dot A, right? But yeah, it's kind of, when I'm finding magnitude of A, it's easier to show this with like Cartesian vectors, I think. Cool?
So that's proof for all.
Yep, all possible vectors.